conclude by talking about extending uniqueness to R. Okay. And this is going to require a little bit more work. Okay. So let's actually take, so we have a way of solving our inhomogeneous heat equation. Let's say, well, we have this solution. Is it unique, right? So x goes from 0 to R, okay? And let's say I'm not going to bound space, but I'll bound time. And I'll say that t is bounded by 1 over 4k mu, okay? I can't get away with everything being unbounded, but if I'm going to unbound space, then I can just bound time, okay? And let's say that I have some initial condition, okay? So we have a theorem that speaks to the uniqueness, and that's that there exists at most one continuous solution to this thing that we call star here, right? Where as long as u of x is bounded from above by m e xp of mu x squared, where x is in R, okay? Where m greater than 0 and mu greater than 0 are constant, okay? All right, so so all this is saying is that as long as I can place some upper bound on my solution that looks like this, okay, then I can assume that there's at most one solution to this PD up here that I've written down, this initial value problem up here that I've written down, okay? So fine, okay. How do we prove this? So first of all, we have to assume, right, that u sub x less than or equal to 0 is also bounded from above by that exponential term there, okay? And I'm going to relax this later, okay? But I can carry forward the proof more easily if I have that assumption in place, okay? And now suppose that u1 and u2 solve star. And we're going to do the typical thing that we do for uniqueness. You can probably guess. I'm going to define something called w, and I'm going to say that's u1 minus u2. So what do we get for w? We get that wt equals k wxx. X lives in R. And again, this is just going to hold on t is less than 1 over 4k mu, okay? It's a pretty generous bound on time, right? Because I can make that mu small if I like. And wx0 equals 0 in that case, okay? And what do we know? Well, based on assumptions, we know that the norm of w and the norm of wx are bounded from above by 2m exp mu x squared, right? By the triangle inequality, right? Because w is the difference of things that are bounded from above by m times that, so I can bound w by twice that amount, okay? All right. So now what we're going to do is going to look somewhat similar to what we did in the case of the maximum principle, which is that we're going to define an auxiliary function v, and we're going to start to prove things about v, and that's going to help us prove something about u. Okay, so let's start by fixing x, y in R and this domain that t is bounded in. And we're going to define v of y tau to be equal to phi of x minus y, t minus tau. Okay, and note that there's this negative sign on tau here. Okay, so again, phi is just going to be our fundamental solution. So you can maybe start to see why I've put this peculiar bound on u. Okay, and you know, because of this negative sign here, right? If I compute v sub tau plus k v y y, that's equal to 0. Okay, because of the negative sign on tau. So using u of y tau, right? What I have is 0 is equal to v times u sub tau minus k u y y. Okay, because that's this thing is going to be 0 because u should satisfy the heat equation, plus u times v tau plus k v y y, which is equal to, by the product u v sub tau plus k u v y minus v u y y. Okay, and sorry, there should be a w here. Let me go back and replace these all with w's. Okay. W tau, w y y, w times that, w times that, w times that, and w y there. Okay, sorry about that. All right, so now what we can do is integrate over y in minus r to r, and tau is in 0 to t minus epsilon, okay? For some epsilon greater than 0 with absolute value of x less than r. And what we'll get is 0 is equal to the integral from 0 to t minus epsilon, integral from minus r to r of wv sub t dy, plus the integral from 0 to t minus epsilon k w vy minus v wy, and fundamental theorem of calculus just allows me to you know, differentiate that antiderivative and evaluate at the boundaries there. So I just have an integral left in terms of d tau there. Okay. I should have a d tau integral here. So what I end up with is the integral from minus r to r of w of y tau minus epsilon, t minus epsilon, excuse me, phi of x minus y epsilon dy is equal to k times the integral from t minus epsilon v wy minus w vy evaluated between y equals minus r up to r d tau. Okay. And remember, I have these growth assumptions on w and wy. Okay. So that means that the right-hand side should go to 0 uniformly for tau is between 0 and t minus epsilon, okay? Because these are going to grow essentially, these are bounded, right? W and y and w are bounded, right? And so when I take these differences here, right, because their growth is bounded, and because I know how v evolves, right? V is defined according to this, which is going to shrink at a rate that is faster than wy, and w can grow. And when I evaluate these things, they're going to vanish at these boundaries, right? Basically as r goes to infinity, okay? So right-hand side goes to 0 uniformly for this as r goes to infinity, okay? So let me sort of fill in the gaps, right? So as r goes to infinity, right, recall that v and vy, okay, are gonna decay like the exponential of minus x plus or minus r squared divided by 4k tau, okay? Essentially faster than e to the mu x squared is going to grows, okay? So this means that the integral over all of r of phi of x minus y epsilon u of y t, sorry, this should be w, right? T minus epsilon dy is equal to 0. Let me look back at this previous page, right? So this thing here, right, as I take the limit as r goes to infinity, I have this integral over the real line. I have my w here. I have my phi here, right? And I'm saying that these terms in here are going to become vanishingly small because of the way that v and vy are going to shrink faster than wy and w grow, okay? So that means that I can write down this relation, which is just that the left-hand side should equal 0, okay, as r goes to infinity, okay? So now finally, if I let epsilon go to 0, then what I have is that 0 is equal to the limit as epsilon goes to 0 from above of the integral from over r of phi x minus y epsilon u y t minus epsilon dy, right? W, excuse me. And that should equal W of xt, right? Because phi is going to go to a delta function as epsilon goes to 0. Okay, so W is equivalently 0. Okay, so that implies that U1 is equivalent to U2. Okay, basically for any X or T. Okay, so that's what we wanted to prove, right? That U1